you remember in the last class we discussed 3-point scattering amplitudes, both for the bosonic string and for the superstring. And we computed basically every relevant 3-point scattering amplitude. Of course, we'd already computed for tachyons before, and then we computed it for massless particles, both for the bosonic string and for the superstring. Any questions or comments about that?
I have one question.
Yes.
So, the 4-derivative action is written 3 terms, R square, R in R.
Yes.
Now, if we are considering up to 4-derivative action,
Yes.
then why we are saying that that gravitational wave what is propagating satisfies only Einstein equation, not the
When we're computing the 3-point function?
yes, and if it satisfies the full equation of motion up to 4th order,
Yes.
does that mean that R and R min is 0?
Okay. So let's say it again.
Perturbative state.
It's a perturbative statement.
Oh, it only affects the leading one.
That's right. You see, we are computing the tree level. We're trying to ask what effective action will reproduce this 3-point function. So in the effective action, this 3-point function, which is order G string, okay, there's some parameter which is epsilon, and we're working to that just to order epsilon. Just it's 3-point functions order string coupling, for instance.
Since this is the last order.
Exactly. Exactly.
Only leading order.
Exactly. 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 If we work to any higher order, that's also the order at which loops are also important. Okay, so just for this classical case. Question. Okay, excellent. Other good question. Other questions or comments? Okay. So today our goal is to now study 4-point functions. It's okay. Who? Anurag is also.
Everyone has gone for the
Oh, ST4. Anyway, if we keep cancelling class, we'll never finish. So people can catch up on that. Yeah. Okay. So now in today's class, what we're trying, what our plan is to study, not just to study 4-point functions. As we remarked last time, 3-point functions are very tightly constrained by kinematics. 4-point functions are much less constrained by kinematics. So the study of 4-point functions is interesting. Okay. So let's start with bosonic string and the tachyon. The nice thing about the tachyon is that there are no indices to keep track of. It's completely unphysical, but it gives you many of the key features in a simple setting. Many of the lessons we learn from here continue through to the superstring for the gravitons. Okay. So before we start the calculation itself, let's do some simple kinematics. Let us remember that the mass square for the tachyon was -4 divided by alpha prime. Okay. Now we define these variables. I can't remember if we did it last time. K1 plus K2, the whole thing square, and we put a minus sign because in our conventions we have
this is
minus plus 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 plus. So this thing would be negative for a time like momentum. So we want okay. So T is equal to minus K1 plus K3, the whole thing square, and U is equal to minus K1 plus K4, the whole thing square. Okay. Now with these conventions, I alluded to this last time, but we'll work it out carefully now. Let's compute S plus T plus U. S plus T plus U. This is equal to 4m square. Let's check that. So it's correct. So this is equal to minus K1 square. You see, everywhere that we have this, we have K1 square, and that will appear 3 times. Then we'll have minus K2 squared, minus K3 squared, minus K4 squared. And then we will have minus 2 K1 dot K2 plus K3 plus K4. Okay. So this is equal to Now, each of these minus k squareds is m square, right? Because our convention is minus k square is m square.
Yes.
Okay, so each of these, so there are how many? 6 of them. So that is minus 4 by alpha prime. Let's write m square, we'll later substitute.
Yeah.
Minus 6m square.
Just 6m square.
Plus 6m, thank you. Plus 6m square. And this is plus 2k1 dot k1, where we've used momentum conservation, k1 square. And therefore, this is minus 2m square. Minus 2. So that's equal to 4m square. And plugging in the formula for what m square was, in our case is minus 16 by alpha prime. Okay. So we have s plus t plus u here is equal to minus 16 by alpha prime. Now Polchinski deals with rescaled STU variables, which we should also use. So let me find what he does. Yeah. Polchinski, instead of looking at S, T and U, actually often works with what he calls alpha S, which he defines to be, he defines the function alpha x to be 1 plus alpha prime by 4x. Okay. So now let's look at alpha s is 1 plus alpha prime by 4s, and similarly with t and u. So what do we get for alpha s plus alpha t plus alpha u?
So is this with a rigid trajectory in mind?
This is with a rigid trajectory. Also, this is to get non-dimensionalize it and to get, you see, part of the reason is what we see here, but exactly, it's a rigid trajectory. Okay, this here, it's what will appear in the gamma function, as we'll see. Okay, this is equal to, of course, 3 plus alpha prime by 4 into s plus t plus u, which was minus 16 by alpha prime. So that's equal to minus 1. Okay, and we will actually often deal with minus of alpha s. So minus alpha s plus minus alpha t plus minus alpha u is equal to plus 1. Okay, so that's part of the reason that instead of dealing with something which has some ugly minus 16 by alpha prime, it's got a minus 1 or plus 1 depending on how you look at it. Okay, excellent. So that was just definitions at kinematics. Notice that because s plus t plus u is some constant, there are actually only 2 kinematical variables. Okay, so now let me remind you also about this thing which is crossing invariance. Okay, at the level at which we're working, actually at loop level it's quite a deep statement. Okay, I think it's worth, I'll take 5 or 10 minutes to tell you about this. First let me tell you in general and then we'll see how it applies here. Okay, see, suppose we've got an S matrix. So we've got K1, K2, K3, K4. Now, suppose this was, your time went like this. Okay, so these were initial and these were final. Suppose that was the situation. In this case, K1 plus K2, the whole thing square minus, is the center of mass energy square of the problem. Okay? And so this is a positive quantity. And in fact, it's greater than equal to 4m square. Right? Because the center of mass energy cannot be smaller than 2m. That's when both of them are at rest. And if they come with some momentum, it's greater than that. Okay? On the other hand, let us look at, let's say, let us look at T. Okay? It's best to look at it in the center of mass frame. So in the center of mass frame, we could arrange things so that the momentum comes in this direction and then scatters by an angle theta. So this was K1, this was K3, this was K2, and this was K4. And you should understand, sorry, K4. Yeah. And you should understand these diagrams appropriately in the sense I'm drawing just the spatial momentum. But of course, there is space-time momentum. Okay? Now, in our conventions, K1, K2, K3, K4, let's say, are always drawn with momenta going into the process. Okay? So, let us write down the 4 momenta for this.
And the 0 components all being positive?
They're positive for the incoming states, yes, and negative for the outgoing states. Because you see, the outgoing states have positive energy while going out.
Yeah.
Okay? So my momentum conservation equation was written K1 plus K2 plus K3 plus K4 is equal to 0.
Yeah.
Okay? Because I want to write it in a democratic way. You'll see exactly why. Okay? So therefore, K1 is, so suppose the modulus of, the modulus of momentum was, let's say, mod K. Modulus of spatial momentum. K1 would be the vector square root of m square plus k square, that's the energy. K1, that's the x component, y component 0, and there's no z component. Everything's happening in a 3-plane. Okay? K2 would be square root of m square plus mod k square. This is, sorry, mod k. It's just k minus k. Just call this k. The modulus of all momenta is k. Minus k and 0. Just opposite direction, same energy. K3.
Will be negative.
Now.
But the outgoing, it has to be positive, right?
Exactly.
Yeah.
So K3 will be this same vector with a cos theta here and a sin theta here, but then everything made negative. Right? Because that's the momentum outgoing, and therefore you have to reverse all signs ingoing. Yeah. Okay, so minus square root of m square plus mod k square minus k cos theta minus k sin theta. Is this clear? Theta is the angle with respect to the initial momentum, the angle of scattering. So it's it's this. Okay, so if you continued K1, what is the angle between K3 and K1? Okay, so if theta equals 0 would mean K3 was collinear with K1. Clear? And similarly with K4, K4 would have been minus this with the sin, cos theta sin theta. But then you have to take minus of that. So is equal to minus m square plus k square, k cos theta, k sin theta. Now with plus. Is that, can you read it from here? Not quite. Cos theta, sin theta. Is this clear? Okay. Excellent. So now, what I'm going to do in this frame is to compute S, T, and U. Just so that everything is totally clear. Okay, S is very simple because S is simply minus of 2 square root m square plus k square 0, 0, the whole thing square. Because S, I just add up this and this. Okay, all this and this. That vector, the whole thing squared. Because of a sign convention, this is negative. So this is 4 of m square plus k square. That was S. That's why S had to be greater than or equal to 4m square. Okay. What about T? T in this case is K1 plus K3 the whole thing square. Now what do you see cancelling? It's the energy part. Okay, so we'll write it out, but immediately you see that T is a space-like vector. So you immediately see that whatever T is, it will have to be negative. Okay, so but let's write it out anyway. So T is equal to k into 1 minus cos theta, comma k sin theta, the whole thing square. So that is equal to, with a minus, so that's equal to minus k square into
k square into 1 plus cos theta.
Yes. 2 minus 2 cos theta,
Yes.
which is equal to minus 2k square into minus 4k square into sine square theta by 2. Okay, or equal to minus 2k square into 1 minus cos theta. So what you see is this. You see that T is essentially, in units of the momentum square, is a measure of the deviation of theta from 1, or more precisely cos theta from 1. Okay, so T is, apart from this normalization, is cos theta, 1 minus cos theta. Okay, in particular T goes to 0 at the level at forward scattering. Okay, and why is that? That's simply because in that case K1 is equal to K3, but outgoing, so K1 plus K3 is equal to 0 if there's no scattering at all.
And U is just backward.
U is basically treating this guy as if it was 3. Okay, when you work out U, you will find that this is exactly minus 2k squared into 1. So U is equal to 1 plus cos theta, which is equal to minus 4k squared into cos squared theta by 2. Okay, so these formulas are true in general for equal mass scattering, are useful to keep in mind, because while it's often, for reasons of relativistic invariance, it's often conventional to write things in terms of ST and U. When you want to think of a scattering amplitude, you often want to think of it in terms of center of mass energy, let's say, or K. So you go to the center of mass momentum, you want to think of it as K, because that's how fast the particles are coming, and theta, because that's how much they're scattering. That's the more physical way of thinking of it, and when you think of scattering amplitude, that's often how you think about it. But you'll often see the answer presented in this form. It's useful to be able to go between them. Okay, the point I wanted to make at the moment, though, was a very limited one. It was simply that both T and U are negative. Okay, it's simply that both T and U are negative when K1 and K2 are the initial states. Now, so suppose I draw a plane with S here and T here. Okay, and I ask what region of this ST plane can corresponds to scattering. Okay, clearly S can be anything, so suppose this is 4m squared, anything to the right of this. Okay, and T here is negative. However,
bounded.
Yes. However, no, but T also, right, exactly. T cannot be too large.
Exactly.
Sorry.
But it's equivalent.
Same thing, yeah. T cannot be larger, its modulus cannot be larger than 4k square. 4k square is the difference between S and 4m square. Okay, so there is this line here, which is basically S is equal to minus T. And all physical scattering happens here. Is this clear? Okay, all I'm saying is that S minus T, S plus T, what am I saying? I'm saying that S plus t is for it cannot be smaller than 4m squared. Okay? That of course you just see from those expressions. Now that's great. This is what happens when k1 and k2 are the initial states. But what happens when k1 and k3 are initial states? Now you see that when k1 and k3 are initial states, okay, the thing that was S, which was initial state plus initial state, is now T. So what old S old goes to T. Okay? And now it's a bit ambiguous about which one is the other one, but let's say that, so let's do the following flip. Suppose I do the following flip. I do the flip 2 goes to 3. That takes k1, k2 being initial to k1, k3 being initial. The thing is, you could also accompany this by something else, but we won't do that. We'll choose this. Okay?
But in order to do that, we have to take care of the zero component of the momentum. The
Yes.
of the zero component.
So this will not be correct anymore. Coming then. So now what we have is that the initial states are k1, k3. So 2 goes to 3. So see, what was S, which was old k1 plus k2 the whole thing squared, went to T, which is k1 plus k3 the whole thing squared. Okay? What was U remains U. Right? But what was T became S. Okay, so this was, so with minus, 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 this is equal to T, this is equal to U, this is equal to S. Okay, so now we have something similar. T in this, what was the scattering when 1 and 2 were initial? Had S positive. Now we have T positive, and in fact T greater than 4m square. So you see, we just extend this line here and shade this region. And that is the allowed region of scattering. So this is where we sample 1 and 3 are positive. 1 and 2 are initial. This is where we sample 1 and 3 are initial. Is this clear? Okay, and we have one last option. The option was that 1 and 4 were initial. Because switching between initial and final, if you have both groups switching between initial and final, nothing changes. Okay? It's a question of how you divide into groups of 2. Okay? So the other option is 1 and 4 was final. So let's try that out. Okay, and just in response to Upmanyu's question, if we were to write down a momentum sample for this thing, we would choose k1 as equal to this, k3 is equal to this, k2 is equal to this, and k4 is equal to this.
Yeah.
Okay, we would just do the flip. Okay, and that's why we conclude that it was only this region. Okay, where S had to be negative and has to be, it's clear, right? And finally, we have 1 and 4 initial. Okay, this involves flipping 2 and 4. Okay, so it involves flipping 2 and 4. Can you see that that will take S to U and leave T to T? Because 1 and 3 just stays unchanged. What? Yeah, okay, let's see. So suppose we take, I'm just flipping 1 and 4. Yeah, okay, let's do it. It may be better just to flip 2 and 3 actually. Anyway, let's just do it. Let's just do it. Okay, so let's flip 1 and 4. So what was k1 plus k2, the whole thing squared, becomes k4 plus k2. Oh, I messed up. Did I want 2 and 4? Yeah, sorry. Let me do it. That's what I meant. That's what I meant. 2 and 4. Yeah, 2 and 4 will do it. Yeah, because the initial should be 1 and 4. Yeah, 2 and 4 will do it. So now this is obvious. S goes to U. Because k1 plus k2 will go to k1 plus k4. k1 plus k4 will go to k1 plus k2. k1 plus k3 will just stay where it is. Okay. So S goes to U and T goes to T. Okay. So as before, the condition is U greater than 0. In fact, U greater than 4m squared. And U plus T is greater than equal to 4m squared. These are the two bounding lines. Okay, but now we've got this plot on the ST plane. We don't want UT. So we'll just substitute what U is in terms of S. Okay, so U is equal to 4m squared minus S minus T. Okay, so here we will get 4m squared minus S minus T is greater than 4m squared. Is less than 0. So S plus T is less than 0. And here what will we get? Here we will get U plus T, so that's minus 4m squared minus S.
And S greater than S less than 0.
S is greater than
Less than equal to 0.
Yeah, so S less than equal to 0. So S is negative, and this S plus T is greater than 0, is less than 0. Yeah. S minus T, sorry. S plus T is less than. It's just obvious, it's just redundant. It's just the whole plane. No, what am I saying? No, something wrong. S plus T. It sounds like it's this part. Did we do it right? My memory is that the answer was this.
Yeah. I mean, the vertical line is cut off in the lower half plane. S less than 0.
Yeah, exactly. So here, my memory was that this was the answer without this part. What?
T was also less than 0.
Why was T less than 0?
No, to start with, U was also less than 0.
U was less than 0, and that gave us.
No. These are just two constraints here.
Yeah.
T goes to me, but T was already less than 0 to start with. So it went to T, which was again less than 0.
Yeah. And how did I get these two constraints? Let me remind. Yeah. Yes. Here we also had to put that T was less than 0, which thank you. So, see, this was this bound, but we also had to put that this bound did not extend here. So, and T was less than 0. This continued to be T less than 0. And yeah, so that matches my memory. Thank you. Perfect. Thank you, Sunil. Okay, so these are the 3 different quadrants of scattering. Now what do you see? What you see is this, that if you wanted to find 1, 2, 3, 4, 1, 2 as initial states, 1, 3 as initial states, and 1, 4 as initial states, okay? Knowing the answer for 1, 2 as initial states is not the same as knowing the answer for 1, 3 as initial states, because there you have to know the function in a completely different region. Okay?
All mutually exclusive.
All mutually exclusive. So this is the first point to remember. Sometimes quantum field theory books give you the impression that if you know any of the answers with any 2 initial states, you automatically know the answers. The first thing to know is that there is some assumption going on. Well, we'll come to the assumption in a moment. Okay? But the first thing to recognize is that in kinematics, you could imagine a function here that had nothing to do with what it was here, and nothing to do with what it was here. Just purely kinematically. However, now we're not just kinematists. We're also complex analysts, right? Okay? And in complex analysis, it often happens, okay? It often happens that if you know a function in some region, and you know that the function is analytic in a suitable domain, then the knowledge of the function in some region is enough to produce the knowledge of the function everywhere. Okay? So, now caution, we're not dealing with complex analysis of a function of 1 variable. We're dealing with a complex analysis of a function of 2 variables. And if you're like me, you've stopped studying complex analysis when it became 2 variables. We're all very familiar with functions, f of z, Weierstrass theorem, all of that. There are analogues of all these things with higher dimensions, and there are famous subtleties for all these things in higher dimensions. Okay? So this is a complicated mathematical question, not complicated for the mathematicians, but for me it's a complicated mathematical question to know what is the, what are the properties that allow you to go between these things. So, some analyticity property. So basically what you need to know is that there is some region in complex, this 4-dimensional complex space, 4 real dimensional complex space, where you can analytically continue between here and here and here, yeah? And then you can prove some theorem saying then it's enough to know that if you know the function here, you can find it here and here. Okay? The claim that actual scattering matrices have the analytic properties needed to make this continuation, so that knowledge of the function here is sufficient to produce the answer here and here, is often made. And it's called, and this property that knowledge of the function here allows you to find the function here and function there has a name. It's called crossing symmetry. Okay? And the claim is often made that, that scattering amplitudes in quantum field theory are analytic have the analyticity properties so that they are crossing symmetric. Now I just want to caution you about some elements of this claim. The first positive note is that if you're computing a scattering matrix at tree level, so that the analytic structure is so simple that the only non-analyticities are poles, then it's very easy to prove this theorem. It's sort of obvious. It's not much proving to do. Okay? So at classical scattering amplitudes, tree level scattering amplitudes, this is just an obvious statement. At loop level it gets less obvious. Nonetheless, there are proofs. There are proofs in quantum field theory assuming that there is a mass gap in the theory, and assuming that making certain other assumptions. Okay, certain other reasonable assumptions. There are proofs for crossing symmetry using the basic principles of quantum field theory. There are no general proofs in string theory. However, Ashok Sen, just by analyzing string scattering amplitudes, the detailed formulas, has shown that modulo caveats, which I'll tell you about, string scattering amplitudes also obey crossing symmetry. Okay? But this proof came only last year, and I emphasize it's something that needed a proof. It was not some obvious statement. Moreover, Ashok's proof is sort of a subtle one. It went this way. It went that the only possible violations of, even in quantum field theory, there is no proof that in a theory with massless particles crossing symmetry is obeyed. And indeed, it may well be false due to certain infrared effects.
I mean, in massless theories, at least in 4D, the S matrix itself is not well defined, right? Because of the
exactly. So that's
theorems and
exactly. That's one element that goes into it. However, in massless theories, let's say of gravitons, in 5 dimensions and higher, The S matrix is well defined.
Yeah.
Yet there is no proof that they, and every case of massless fields I think has to be dealt with by itself, because it could lead to new subtleties. Infrared effects could lead to properties of these things that violates crossing symmetry. Okay, so Ashok's proof really went like this. He wrote down some sort of effective action for the massless fields. He left the integral over the massless fields to be done. That was quantum field theory, because there's just few degrees of freedom. The rest of the amplitude was crossing invariant, and then any issues arise just because of effectively field theoretic degree issues with long distance. So he proved that that string scattering amplitudes obey crossing to the extent that you should expect them to. It's a slightly nuanced statement. Okay, none of this is going to impact our analysis for the next few lectures, because we're going to be talking mainly about classical amplitudes. But I just wanted to set the basic picture in place. This is what people mean when they talk about crossing symmetry of scattering amplitudes, and I just want to emphasize once again that this is not some automatic thing. Okay, it's often true, but it's not something that is obviously true. It needs a proof. In classical theories, it's basically obviously true. Okay, is that clear?
For trivial amplitudes, there are particular mathematical proofs which prove this. I mean,
Yeah, it's very simple. The fact that they're only poles, it's just basically obvious.
I have a question.
Yes.
So I believe the Katkowski rules
Mhm.
are sort of closely tied to the crossing symmetry.
No,
Is it?
unitarity.
Okay.
Katkowski's rules are unitarity.
Right.
That is a separate issue. Okay. Okay, now let's move on. So now that we've got the kinematics of four particle scattering state, we've got crossing symmetry state. Yeah. Now, we're just going to move on. Okay. Basically, in things that have whose function, all the issues arise when there are branch cuts. All the issues with this thing arise when the branch cuts. When you're going from here to here, which branch do you choose? You go up or down, and then there are multi-branch cuts. Those are all the issues. With poles, there are no such issues. So it's just some obvious thing. With poles, it's basically the statement that the thing is manifestly an analytic function of ST and U, and crossing symmetry is just a statement of permutation invariance. Okay, it's just the statement that under the okay, I'll say this last thing. Under permutation, you see, we've got this K1, K2, K3, K4. If everything's analytic, it doesn't matter whether, whether K1 plus K2 squared is positive or negative, and so on. So this whole function here should be invariant under permutations of these four objects. Now, so you might think this tells you that the whole scattering amplitude is S4 permutation invariant. Invariant has invariance under S4, the permutation group of four objects. Okay, but there is a part of this permutation group that does not affect ST and U. And that is this. Suppose you take 1 goes to 2 and 3 goes to 4. Then S, which was 1 plus 2 the whole thing squared, now becomes 3 plus 4 the whole thing squared, which is same as 1 plus 2 the whole thing squared by momentum conservation. T, which was 1 plus 3 the whole thing squared, goes to 2 plus 4 the whole thing squared, which is same as 1 plus 3 by momentum conservation, and so on. You can convince yourself that any flip of two particles, 1 goes to 3, 2 goes to 4, or 1 goes to 4, 2 goes to 3. The same thing is true. So these Z2 times Z2 flips do not change STU. So the actual invariance of the problem is invariance not under S4, but the part of S4 that is cosetted by this group Z2 times Z2. Okay, these three elements plus identity make a subgroup. It's an abelian subgroup of S4, and it's just a mathematical fact that we could spend time on, but I won't bother. S4 modded out by Z2 times Z2 is equal to S3. You can check dimensions. S4 is 24 dimensional. Z2 times Z2 is 4 dimension. Yeah. mod out, you get a 6-dimensional group which is S3. This is some mathematical fact that you could convince yourself is true. So the actual invariance here is under S3 permutations. And how does S3 operate? Well, one way of thinking of it is that these Z2 times Z2 permutations can always be used, given any permutation, to freeze 4. Do you know what I mean? What I mean is that you've got these Z2 times Z2 permutations, and these Z2 times Z2 permutations, for instance, take 1, 2, 1, 2, 3, 4 to, for instance, 2, 1, 4, 3. Now, give me a permutation. Shuman, name a permutation. 1, 2, 3, 4 goes to just name. 3. Okay. Okay. Now, take any such permutation. I'll find a Z2 times Z2. In this case, 1, 2 with 3, 4. That takes 4 to 4. Say I do the 1, 2, and 3, 4 Z2 times Z2 flip on this. That will make it 2, 3, 1, 4. It's all, wherever 4 was, I could have chosen the Z2 with 4 and that object to put 4 in one place. And but then I've used up my Z2 times Z2 invariance. I've fixed gauge. Yeah. Okay, so what remains is S3. That's really the proof that this is S3. Okay, when you do the gauge fixing, you get S3. Okay, now, so you can always think of it that way. Let's freeze 4, or let's freeze 1, because 1 was the special guy now. Let's freeze 1 and permute 2, 3, and 4. But you see, if I freeze 1 and I permute 2, 3, and 4, what I get is all possible permutations of STU. So, the real invariance of this problem is that the amplitude, scattering amplitude, is invariant under all possible permutations of STU. S goes to T, T goes to S, U to U, or a cyclical permutation, S to T, T to S, T to U, U to S. All possible permutations of these 3 objects. That's how S3 acts on these, are the invariance of the amplitude. So whatever the amplitude we have has to be a completely symmetric function in ST and U. As long as it has only poles, that's all that you have. When you have cuts, life becomes more difficult because there are you have to choose branches. Okay? And there are more subtle statements. This could be that this branch with S and T is that branch with T and U. So on any given branch, it may not be completely symmetric. Do you understand what I mean? Because there's a choice of branch also involved. Anyway, we're not talking about quantum amplitudes at this point, so we can forget about the subtleties now. For us, it's just the simple statement that crossing invariance implies permutation invariance in STU.
Z2 cross Z2 means it will permute first 2 and second 2.
For any group 4 objects into any group of 2 and 2 and flip those 2.
Okay. That's the
Independently.
Flip both of them.
So everyone is changing. So if you fix one, then
Yes.
you are fixing the gates.
Exactly. Exactly. There are 4 elements in Z2 times Z2. One element is just identity, which is nothing. The next element, there are 3 ways of breaking 4 objects into groups of 2. Because 1, 2, 1, 3, and 1, 4, and then the remaining ones. Okay, then once you've broken into groups of 2, you have to flip both. That's what Z2 times Z2 is.
Sorry, what is the identity for Z2 plus Z2?
Identity is doing nothing.
Nothing.
Take 1, 2, 3, 4 goes to 1, 2, 3, 4. Identity for all groups is the same, does nothing. Okay, so is this clear? So the end result of all of this is that the whole amplitude, if it is symmetric in ST and U, has all the permutation, has the full S4 permutation invariance.
Sir, I have one
Yes.
question. I mean, so it's surprising that a proof of in quantum field theory of the crossing symmetry does not exist. I mean, I was just
Well, it exists provided there's a mass gap.
okay. I see.
In theories where there is a mass gap, it exists.
To all loop.
Oh, it's a non-perturbative proof.
I see. Yeah, I mean, I was just thinking of a path integral argument that let's say if you insert some let's say for simplicity, all these identical operators in the path integral, and then we just redefine each of these, and the path integral remains the same with this insertion.
Yeah.
So this might be
The difficulty with this is choice of branches.
I see.
You have to make sure that this is doing the right branch thing.
Okay.
Because these functions become multi-valued because of branch cuts.
Hmm.
You have to know what you're talking about. Okay, so there are subtleties associated with those things.
So a general proof would consider non-perturbative effects.
Actually, it's abstract. The general proof is an abstract proof. It just uses causality. It uses this thing called the edge of the wedge theorem. It uses general properties that operators commute outside light codes. Okay, the LSZ formula to prove a certain region of analyticity. Okay, then it uses mathematical complex analysis to show that if any function is analytic in this domain and has certain other properties, then it's analytic in a larger domain. And that larger domain of analyticity then is enough to show.
Provided, of course, that it does not cross any singularity or any branch. I mean, it's provided it remains within one branch.
Yeah, you know, all of that is taken into account. They talk about the first sheet. It's some complicated thing. For instance, were you at Ashok's talk?
Yeah.
He reviewed this proof in the first few slides of his talk. So it's some old 60s, 70s proof. It assumes a mass gap, but and it assumes certain things. But it's quite a general proof. Making, never using Feynman diagram analysis or anything like that. It's just very general properties. Right. Okay. Can also be proved diagram by diagram. In reasonable, in Feynman diagrams that are, all of which are massive. That's roughly what Ashok did. He did it for string theory, but string theory is diagram by diagram, basically, because it's perturbation theory. Okay, excellent, all excellent questions. But, for our limited purposes at the moment of doing tree-level scattering, you can just forget about it. All we want to do is impose this permutation invariance. Do you understand that we just have to make the function completely symmetric in STU? Okay, please.
These three are the only elements of this Z2 plus Z.
These three plus identity.
With identity.
Yes. Because Z2 times Z2 is a 4-dimensional group. Okay? Excellent. So let's keep going. So now that we've, all of this discussion for us is really moot, we're just going to write down a scattering amplitude as a function of ST and U and make sure that it's fully symmetric in ST and U. Well, it'll turn out automatically to be, but that it was will be sort of interesting. Now I'm going to say one last thing. We better get to the answers as well. But okay, let me say one last thing. I'm saying all these things because these are the things. When I studied string theory, the formulas were very easy to get, but these general pictures took me a long time to figure out. So all these simple general things that every reasonable physicist knows when he's old somehow don't always get communicated to students. Okay. Okay. I'll tell you one last thing. Is the statement of crossing symmetry, but there are no branch issues. It's just that it's completely analytic with no complications. Because it's completely analytic, you can just flip ST and U. Then it's exactly what you were saying. It's just a flipping symmetry in the path integral. So as long as your answer was invariant under that, which in the path integral obviously is, okay, then you're done. Okay. Now this was this last general thing I wanted to tell you, and what was that? No, what was that? Yes. There's one last thing I want to tell you, which is this. Suppose we have a theory, okay? Suppose we have a theory in which our scattering amplitudes have a bunch of poles. This will be the case in string theory, this is why we're studying it. In string theory, we've got this whole closed string spectrum, and when we scatter tachyons, many particles in this closed string spectrum will be exchanged. Okay, strings of arbitrary mass in the spectrum will be exchanged. So we're going to have poles in S. Okay, so suppose we've got some theory which has some poles in S. Okay, so this will be whatever it is, some function of, let's say, t divided by S minus mi square, sum over I, for all the particles that are being exchanged in the problem. We're going to have scattering amplitudes that will have structures like this. And these will be the only allowed non-analyticities in the problem in S. The only associated non-analyticities in the problem classically associated with poles in S. But because the whole problem is because the whole problem here is symmetric in S and T, you must also have similar poles in T and similarly similar poles in U. Okay, but now there is this very beautiful thing, which is this. Think of this function here as a function of S and T. Okay? In particular, I want to think of it as a function of S at fixed T. Okay. Now, suppose I know that at fixed T, this function decays sufficiently fast at infinity.
In the high, okay. Not at necessarily the high end.
Yeah. At S goes to infinity.
Yeah, that's what I meant. I'm not at.
S goes to infinity, but everywhere on the complex plane.
Yeah.
But at fixed T. Suppose I know how it decays sufficiently fast. We'll come back to how fast is needed. Okay, but suppose I know that it decays sufficiently fast. Then I can start, then this function is uniquely characterized by its poles and residues at poles. Why is that? Suppose this whole function at fixed T, I think of it as S. Whatever it is, I think of it as S. There's some T, but I don't emphasize that because I'm thinking of it as one variable problem because I don't know how to do two variable complex analysis. Okay, so I fix T and think of it as S. Okay, now using Cauchy's theorem, we can always compute. You take a little loop here, and this
On the S plane.
right. You take a little loop on the S plane around the point S. Okay, and we have f of z over z minus s, and then the right factors of 2 pi and so on. 1 by 2 pi I is equal to f of s.
Now this has become complex.
What?
It's become complex.
S can be any number, any object. It could be just any place as long as we've chosen this loop so that it surrounds no other singularities. But in this function, what are the singularities? This function of z has poles wherever it does,
But
at mi square.
Not anywhere in the disk.
Not in my disk, but here it has some poles, let's say. And of course, it has a pole at S. So the poles in Z are at the various points in mi square and Z. Now I take the same function and I do the contour integral here. If it dies fast enough, now you see that we only need for it to die anyhow. Any z to the power minus alpha, no matter how small alpha is, will kill it, because here this thing near z equals infinity becomes 1 by z. That gives a finite answer, polar infinity. But any decay further than that would just kill it. So as long as f of s decays at infinity, but everywhere at infinity. So let's be conservative and say that f of z, no, it goes like 1 by z to the power alpha greater than 0. Suppose we know this is true. Then at least it will work. Could work more generally. Because the power has the feature that decays everywhere at infinity.
I mean, just one concern.
Yes.
If alpha happens to be any real number, then there could be some issues with branches.
No, it doesn't matter, because the answer, just the modulus of the integral is 0. So the modulus of an integral is 0, we don't care about its phase rate. Yeah. So f of z is less than, let's say mod z is less than equal to, fine. Yeah, less than equal to doesn't even make sense for a complex number. Okay, that's what I meant. Sorry. Yes, thank you. Okay, so in that case, we can take this this whole integral evaluated at infinity is 0. Now we can deform the contour so that we get the contour here and the contour around each pole. Okay? But the contour around each pole picks up all the residues. But the residues we assume we know. So this gives us then a formula for this, which is f of s. F of s in terms of the residues at each pole. Basically it tells us that f of s is this sum. What have we proved? We've proved that if we know that f is a function that decays at infinity and it has these kind of poles,
then we can fix the
then the full answer for f of s is just exactly this sum. You see, because that's what the sum over the residues gives. That gives this sum, and this part gives f of s. For f, I'll say it more clearly. We started with a contour. Final statement was this plus this plus this plus this plus this is 0. Therefore, this up to some sign is equal to this plus this plus this plus this. But this just picks out the residues, which is this. Okay? So basically is the statement that if you know the residues, you know that it has poles with certain residues, then just the residues and their pole contributions, there can be nothing else provided the amplitude decays at infinity. Okay? So this is very powerful because you see in general, I mean it's not too surprising. All I'm saying is the following. Suppose this had not been true, then you see, suppose I had this function, and suppose Schumann gave me one function which had the property that it had poles at these points and these residues. And Upman, you gave me another which had poles at these points but the same residues, but the functions were different. Then the difference between these two functions has to be analytic. But we know that the function decays at infinity. Then there's only a unique analytic function that decays at infinity, namely 0. So that's all I'm saying, right? Okay, I mean, I said it in a complicated way, but it's an obvious thing. Okay, so if it does turn out to be true that our function decays at infinity, and we will see in string theory it turns out to be true. Okay, then it had better be that the answer here was simply the sum over s poles. Note the sum over s poles, as we will see, will have analytic functions in T. We will see that happen. And now we're in grave danger of reaching a contradiction. Okay? We're in grave danger of reaching a contradiction because I've told you two things that sound like they both can't simultaneously be true.
But you have a pole in T also.
Exactly. We must have a pole in T and a pole in U because the whole thing has to be permutation invariant. But I've told you that you can't just add those poles in T and U because this is the full answer. So you know the way string theory does this, and we will see that that's part of the miracle of this game.
All the inequivalent diagrams are actually the same string diagram.
That's maybe some interpretation, but the way that string theory does this in this formula is that this summation is infinite. Okay? And there are different representations, different infinite sum representations of the same function. One is as a sum over s poles. One is as a sum over t poles.
So if you sum over T sums and you will get the pole.
The pole in T, exactly. Exactly. You get the poles in T when you do the infinite sums. Each of these is analytic functions. As you said. You know, yes, as you said, it's 1 plus s square plus 1 plus t square plus t. It gives you 1 over 1. Okay? So string theory does this in this very beautiful way where you've got a single function which can be represented just as a sum over s poles and nothing else. Or just as a sum over t poles and nothing else. Or just as a sum over u poles and nothing else, but it's all the same function. It's a remarkable function that we're going to encounter today. Okay, that's all for the generalities. Now let's get to the calculation. Any questions or comments?
But where did this analysis of f of t, the residue, come into
Where did that come? I will show you, but it comes actually more generally. Why does it happen? This is a good question, and it's again taking us to generalities, but let me tell you about it. Okay, you see, what the question that you get, this f of t is not arbitrary, but is fixed by the nature of the particle that is being scattered. Okay, suppose you've got a spin S particle, a particle which has S indices which are completely traceless. Okay, so some particle which is S mu1 to mu S. Okay, these indices are all traceless because if it had trace paths, it's actually admixture of spin lower than S.
Yeah.
Completely traceless, and it obeys the condition del mu S is equal to 0. Where does that come from? Well, that is basically the equation of motion for a spin S particle. Spin S particle obeys two things. A, it obeys something like this, and B, it obeys that del squared S is equal to m squared. Why is this the equation of motion? You can think of this as little group analysis. If you do little group analysis and ask what is the spin S little group representation of the Poincare group, you'll find this. I won't go into that. Okay, it's a purely group theoretic statement. Okay, now how can such a particle couple to two scalars? Sort of obvious, right? We've got, let's call this two scalars phi. We've got 5. You see, this part is coming purely from the 3-point couplings of the two scalars with this spin S particle. Okay? Now, these 3-point functions need only be computed on shell. Why? In actual Feynman diagrams, these two are on shell, but this is off shell. So why am I saying it's sufficient to compute it on shell? It's sufficient to compute it on shell because you know the off shell part and the on shell part differ by a factor of S minus m square.
Yeah.
Because if S is equal to m square, you're on shell. So the difference between the off shell and the on shell amplitude will result in an analytic contribution to the S matrix. And analytic contributions are what we constrain by the behavior at infinity. If you know the residues, we are only interested in the residue of the pole. We're not interested in analytic things. That's another way of saying. Residue of the pole is purely on-shell data. Okay, so we need to know the 3-point on-shell coupling of this. Is this clear? Okay, now, so we've got mu1 to mu k. Now, let me do this in momentum space. This is k1, this is k2, and this is minus of k1 plus k2. Notice that each of these indices dotted with k1 plus k2 is 0 because of this equation. So there's only one momentum that it can dot with, just k1 minus k2. Okay, so the only on-shell coupling that you can have is k1 minus k2 to the power mu1, k1 minus k2 to the power mu2, k1 minus k2 to the power mu s, and then the polarization for the spin S particle, which is mu1 to mu s. Now if you want to get the exchange diagram, at least the pole part of it, what you do is to take this on-shell coupling, a similar on-shell coupling here, and sew them together using a spin S propagator. Okay, so what you will get is k1 minus k2 mu1 up to this. Similarly, k3 minus k4 nu1 up to nu s. And then there's the propagator. It will not surprise you, of course, that the propagator has an s plus m square. That, of course, maybe minus s plus m square, the way we write it. But what about the index structure? Well, the index structure is basically like identity, but in the spin S sector. So it's simply identity, but you know the projector for all indices to lie in the spin S sector. I can make that precise if you want, but I won't try to do that. Okay, some projection operator. Okay, and now scattering by spin S, scattering by particles of spin S now has a fixed momentum dependence. You can see immediately here that the net powers of k never k squared never exceed s in the numerator, because there are sk's and sk's, so sk squares. So if you've got a pole like this here, the maximum power of s that can appear is s to the power of, s to the power, we'll call it j, the spin of the particle. Is this clear? So scattering with a spin j particle intermediate cannot, the residue here cannot grow like faster than t to the power j. Now we use a second property of string theory. The second property of string theory is this. It is that the lightest spin j particle occurs at oscillator number j or j plus 1, j minus 1, j minus 1. Why? Because the lightest way to get spin j, okay, is to take del x mu, del x mu, del x mu. So every time you add a spin, you add one oscillator number. You can of course get, by taking del x mu, you can of course add oscillators without adding spin. But there's never a way to add spin without adding oscillator. You can also add, you can take, instead of del x, you can take more derivatives on x. That also.
There's some reducible components of the lower.
But even if that had not been, it would have just been adding more dimensions without adding more spin. Yeah. It's just totally obvious that you cannot add more. For every unit of spin, you have to add at least one, one oscillator number. And therefore, at any given oscillator number, let's say n, the maximum spin here is n. Now there's a plus 1 because the tachyon starts at level 0. So spin 1, and then there's one extra because we have open string, left and right movers. So at level 1 you're allowed spin 2.
When we consider
closed string. At level 2 you're allowed spin 4, at level 3 you're allowed spin 6, and you make that the general formula. But it's clear then that any given m, there is a bound on the power of t.
Yes.
Just these general considerations. And therefore this is a polynomial which is bounded, of degree which is bounded by that. Okay? So that is what the general principle, and a little knowledge of string theory tells you that those were analytic functions. And so string theory, if it has to give rise to a good scattering amplitude, has to somehow behave very clever. It has to do something extremely clever. And that is what we're going to see string theory manages to do. Okay? So now let's get to the calculation. Since we're doing the calculation in the bosonic string, the calculation is entirely trivial. Since we spent much of the last lecture checking the ghost contributions, the Z1, Z2, Z3 dependence always cancel once we took ghost and other things in account, this time we'll just believe it. Okay. It's easy to check anyway, but we'll just believe it. So what we'll do is this. We take the particle at K1 and put it at Z1 is equal to 0. Okay, so this is e to the power I K1 x of 0. Then we will take the particle e to the power I K2 and put it x at 1. And we'll put e to the power I K3 and put it at x at infinity. So we choose 3 points, 0, 1 and infinity. And then the fourth point
has to be integrated.
Exactly. So e to the power I K4, and then we have x at z. Okay. Now in this case, we've dealt with the C ghosts by fixing these guys. We really should have put them at arbitrary points and checked that the Z1, Z2, Z3 dependence went away. It does. Forget about it. Okay, there are no B business. There's no, because there are no moduli in the sphere. So all that's left is to compute this 4-point function and then to integrate it over Z. It's that simple. So let's look at this 4-point function. So it's the 4-point function of e to the pi kx of 0, e to the k1x, I k2 x at 1, e e to the pi k3 x at infinity, and e to the pi k4 x at z. Now for a moment I'll do the 4-point function calculation at z1, z2, z3 and z, and later take the limits, because otherwise we might get the infinity wrong. Okay, all I'm going to use these special points for is really to knowledge that the C goes to cancel. Okay, so let's first do it in general, and we use our general formula. So our general formula was e to the power I sum over pairs k dot k for the pairs, and then I, so minus sign, no factors of 2, so minus sign x zi x zj. Okay, and because of normal ordering we won't let I equal j. Okay, and then we use, of course, this fact that this 2-point function here was at minus alpha prime by 2 log zij mod square. Okay, and so what we have is mod zij to the power alpha prime by 2 ki dot kj, and some overall product over all pairs. Okay, now the first thing that's a bit dangerous is that one of these z's is infinity.
Yeah.
So that better be that the powers of that thing is 0. Otherwise we're going to get something crazy. Okay, so let's look at the terms that involve z4. Sorry, z3. Okay, so the terms that involve z3 are z3 1. Now, but you know, because z3 is infinity, z31, z32 and z34 are all the same. They're basically z3. So we'll just write that. Mod z3 to the power alpha prime by 2 k3 dotted with k1 plus k2 plus k4. Yeah, what it does look like it's working. Just a minute. So that's z3 alpha prime by 2 into minus k3 square. What have I missed? That's not giving 0. Just a minute. Just a minute.
The incoming and outgoing states, are they defined like defined here?
Yeah, it's just analytic. I mean, it doesn't matter. Just 1 minute. I missed something simple. Just what have I missed?
This is between 1 and 2 and 3 and 4.
Well, no, this is between 3 and 1, 3 and 2, and 3 and 4. I've taken everything into account, right? Just 1 minute. Just 1 minute. Just 1. Let me miss something stupid. Just a minute. Okay, let me put the C ghost contribution. I'm sorry. Let me put the C ghost contribution in. also. It's not going to matter, but I also have to take, sorry. There was also the C-cross contribution, which was Z12 mod square, Z13 mod square, Z23 mod square. Okay, for my special choices of 1, 2, 3, this is 1. All right, let's look at the 3 dependence. This is Z3 mod to the 4. Okay, now hopefully it will work. You see, so now we have Z3 minus alpha prime by 2 K3 squared plus 4. Yeah, so of course we have to take the C-cross contribution into account for this particular choice of Z's. We're going to assume that it doesn't matter, but of course we have to take into account what the C-cross gives for this particular choice of Z. I was just being stupid.
To cancel it, it is.
Yeah, exactly. So now let's see. So K3 squared was equal to
4 over alpha prime.
but this is let's see if now I've messed up this. This is 2 and 2. So if I actually wrote mod, then this 2 should not be there, because this square comes out here. So this 2 is not here. So this 2 is not here. So this is K3 squared, which is now
4 over alpha. K3 squared
is 4 over alpha prime. 4 over alpha prime, and now that cancels, because we get minus 4 plus 4. Okay, Z3 dependence goes away. Sorry about that mess up. Okay, great. Now what remains about the C hosts? It's just mod Z12 squared.
I want us to be careful about taking the order of limits here. First we have to take the exponent to 0 and then take Z3 to infinity.
Which exponent is 0?
No, I mean the exponent of Z3, I mean that's exactly 0.
Yes.
But I mean,
yes.
Infinity to the 0 is an ill-defined.
Yes. So we evaluated at finite Z3
Yeah.
and then take Z3 to infinity.
Yeah, but the order of limits.
Yes. Okay. So the amplitude here now becomes what? What about this mod Z12 squared? For our special choice of
1
is 1. So there's nothing. So now the C-cross contribution has really gone away. And now what we need to do is this product over is everything not involving 4, not involving 3. Okay? So we get Z12 mod to the power alpha prime K1 dot K, K2. No, K1 dot K1 dot K2. And then we get Z1 K1 dot, Z1 4, K1 dot K4, because 3 has been taken out.
Yeah, sorry.
And we get
Z2 4. Z4
mod
3. 3 4.
not 3, 2 4.
Sorry, C was infinite.
Yes. K3 dot K4. This was K1 dot K4, this was K2 dot K4, thank you. And both of them have an alpha prime. By 2 has gone away because of corrections. Okay, now we put in what Z12 was, that was 1. So that's gone. What about Z14? That was just Z to the power alpha prime K1 dot K4. And this is 1 minus Z, or Z minus 1, let's say 1 minus Z to the power alpha prime K2 dot K4. Now all that remains is to see what this guy is. Okay, but K1 dot K4
U plus U over 2 plus something.
is, K1, so let's do it exactly. See, K1 plus K4, the whole thing squared, was equal to minus U. Now, this quantity was K1 squared plus K4 squared minus plus 2 K1 dot K4 was equal to minus U. And therefore, K1 dot K4 was equal to minus 4 minus K1 squared minus K4 squared by 2.
Minus U, that's not 4.
Minus 2, thank you. Okay, and we have alpha prime k1 dot k4, so alpha prime, so there's an overall factor of alpha prime. Okay, now we plug in what a k1 squared and k4 squared is.
Both are 4 over alpha prime.
Both are 4 over alpha prime, exactly. And so we get alpha prime into minus u
Minus 8 over alpha prime.
minus 8 by 2 over alpha prime. Okay, so that's equal to minus u alpha prime by 2 minus 4. Okay, and now Polchinski's definitions. Right. Okay, I'm going to now. Okay, so now we will write this in terms of his. Can somebody remind me what were those alphas? Alpha of u was equal to 1 plus alpha prime by 4 x. Okay, so this I will write as minus alpha prime u by 4 times 2 minus 4, which is equal to minus alpha prime u by 4 minus 1 times 2 minus 2, which is equal to minus alpha of u 2 times minus alpha of u minus 2. Okay, so that's what we got from k1 dot k4, and here we will get k2 dot k4, which is same as k1 dot k3, so the same thing with t. Okay. So the final answer is integral d to z mod z to the power minus 2 alpha of u minus 2 1 minus z mod 1 minus z to the power minus 2 alpha of t minus 2. This is the final answer for the scattering amplitude.
The Euler beta function.
Right. Now, firstly, some of you are thinking this is very odd, because this integral clearly has a symmetry and u goes to t. How do you see that? You just make the change of variable, z goes to 1 minus z. That will flip those two terms. U and t is clearly symmetric, but what about u and s? Exercise. Find a change of variables. That takes this to d2 z prime mod z to the power minus 2 alpha of s minus u into 1 minus z minus 2 alpha of t minus. It's not as simple a change of variables as z goes to 1 minus z. It involves some inversion. It's an SL2. SL2 Z transformation. But find such a transformation that does this. It's, basically
The point at infinity has been.
Well, at the moment, I'm just asking you to interchange. Yeah, exactly. I'm just asking you to interchange 3 and 1.
Yeah.
So the transformation that does that is the transformation that takes z to 0 to infinity and infinity to 0.
1 over z.
So 1 over z will do it. And note that it leaves 1 fixed. So 1 over z will be the transformation that does this. So, but anyway, try it. Okay. So, so this integral is not manifestly symmetric in ST and U, but it is symmetric in ST and U. Okay. Now, this integral is an integral you'll find in the table of integrals. If you wanted to do it yourself, the trick is the following. You use the formula a to the power b. You use the formula that this is equal to, what is it? a to the power b t to the power, you use this formula, t to the power n e to the power minus at is equal to a to the power minus n times n gamma of n, right? Or maybe gamma of n plus 1.
Yes.
Okay, you can use this formula for appropriate values of n to take each of these powers and put it in the exponent. Okay, at the price of introducing two new integration variables, one t for this guy and one t for this guy. Then the integral over z is a Gaussian integral because it's up in the exponent. You do that Gaussian integral and then you're left with the two integrals over the two real numbers, t1 and t2, and that will turn into one of these beta function integrals that you are familiar with. And you will be able to show the following, that integral dz, d2z, z to the power, mod z to the power 2 minus 2a minus 2, mod z 1 minus z to the power minus 2b minus 2. Oh, 2, sorry, not minus 2, 2a minus 2 and minus 2b minus 2. So this is a general formula I'm giving you, is equal to gamma of a, gamma of b, gamma of c, divided by gamma of a plus b, gamma of b plus c, gamma of a plus c, with a 2 pi, where
C is
a plus b plus c is equal to 1.
That is the minus alpha.
That was the minus alpha. That was the thing we saw right at the beginning, that minus alphas obeyed the condition minus alpha plus minus alpha plus minus alpha was equal to 1.
Symmetry of ST.
It proves the symmetry of ST. This is just the answer. Okay. Therefore, with this general formula, we get the answer 2 pi into gamma of minus alpha of S, gamma of minus alpha of U, gamma of minus alpha of T, divided by gamma of minus alpha of S minus alpha of U, gamma of minus alpha of S minus alpha of T, gamma of minus alpha of U minus alpha of T. This is the full scattering amplitude. This is the full scattering amplitude here for 4 tachyons. Now, Upmanyu would like to go for this colloquium, so I think we'll just break here because this is a beautiful formula and we need to study the physics that comes from it in a great deal of detail. Okay, so we won't do that in a hurry, we'll do that next class. So that will be the starting point for the